Shall we start? Okay, welcome back everyone after lunch. So this afternoon's session is titled, Is This Universe Unique? And as per our format, we'll have two people speaking. The first of whom is Bernard Carr. Bernard Carr is Professor of Mathematics and Astronomy at Queen Mary, University of London. His research interests include the early universe, dark matter, general relativity, primordial black holes, and the anthropic principle. He has many prizes, awards, etc. I'll skip all of that and sort of give you one relevant, interesting fact is that he's been the co-holder of a grant from the John Templeton Foundation with Martin Rees and Neil Turok for a project entitled Fundamental Physics and the Problem of Our Existence. And this was used to support a series of conferences, very successful conferences that they held at Cambridge. And he's the editor of a book titled Universe or Multiverse. And that book is based in part on these conferences. So it's a great pleasure to invite Bernard to kick off this afternoon's session on Is This Universe Unique? Bernard?
Thank you, Priya, and it's a great delight to be here. So the topic of this afternoon's session is the universe unique? And of course, I guess because of the nature of this meeting, one can ask that question from the perspective of either science, philosophy, or theology. Obviously, I'm going to focus mainly on the scientific aspect, but I think it's worth bearing in mind that actually, to me, what makes this topic rather interesting is precisely the one that it really is. It does involve an intersect of science, philosophy, and theology. It's clear that the question can be addressed from all three sides, which is why it's interesting that we're all here together for this meeting. Obviously, the philosopher, Tim will be talking after me, but I'm going to focus on the science. And just to say just a little bit, though, about the multiverse in philosophy and religion. The person who apparently first introduced the word multiverse, was actually William James, who, of course, was a philosopher and a psychologist and a philosopher of religion. In his Will to Believe, he says, visible nature is all plasticity and indifference, a multiverse, as one might call it, and not a universe. Well, of course, he wasn't using the term in precisely the way we would use it as a cosmologist, but it's interesting that William James, who was, of course, so interested in religious experience, was the first to use this phrase. And actually, if you read through various religious texts, especially from Eastern religion, there are all sorts of references to things which might be described as the universe. Here is from a Hindu, quote, there are innumerable universes besides this one, and although they are unlimitedly large, they move about like the atoms in you being God, therefore you are called unlimited. Here's something more from Islam. Fakir al-Din al-Razi, in his Matalib, raises the question of whether the term worlds in a Quranic verse refers to multiple worlds within this single universe or to many other universes beyond the known universe. So this is going back to the 12th century. And this is the quote, he, the Most High, has the power to create 1,000,000 worlds beyond this world, such that each one of those worlds be bigger and more massive than this world, as well as having the like of what this world has of the heavens and the earth and the sun and the moon. The arguments of the philosophers for establishing that the world is one are weak, flimsy arguments founded upon feeble premises. That, of course, I'm sure is not true now. But anyway, I'm just trying to make the point that, like many ideas in cosmology, there are parallels within it from the philosophical and religious side as well. But I'm just going to focus on the issue of from cosmology, the role of multiverse in cosmology. I wanted to say a little bit about science and religion, only in so much as I've just attended a meeting in Cambridge a few months ago about Lemaitre. And Lemaitre made such a fundamental contribution to cosmology, and I'll refer a little bit to it. But of course, the remarkable thing about Lemaitre was that he was also a priest. And so often one thinks of Lemaitre as the sort of embodiment of the person who shows that you can reconcile science and religion. But the interesting thing about Lemaitre is that actually, although he was a priest, he always kept very separate his interests as a cosmologist from his interests as a priest. He regarded religion and science as different paths to the truth. Nevertheless, I personally do think there's an overlap of interest in the subject. I've always thought that the fundamental difference between cosmology and religion in some sense is that cosmology is independent of space but time dependent. In other words, all cosmologists believe the same thing wherever they are, but their views vary with time. Whereas, of course, the features of religion is that they tend to be depend on space where you are, but they tend to be, the dogma tends to be fixed in time. So there's a sort of the interesting asymmetry between. That doesn't mean I feel that any dialogue between cosmology and religion is doomed. But anyway, let me now get on to the question of the multiverse. And I guess Priya kindly mentioned it, so I have to say something about my book, Universe or Multiverse, which has just come out in paperback recently, and it's much cheaper now. Let me just summarize what the book says, because it will relate to quite a lot of what I say. Recent developments in cosmology and particle physics suggest that our universe, rather than being unique, could just be one of many universes. Since the physical constants can be different in other universes, the fine-tunings which appear necessary for the emergence of life may be explained. Now, I should say the point about the book is that it actually has contributions from cosmologists and philosophers and theologians and particle physicists. It is not a proselytizing work. It is not saying the multiverse is true. It's got a question mark next to it. There are advocates and counter-advocates, etc. But at least these are the themes which I'm going to address in my talk. And so, just in case I don't get to the end of my talk, or you don't get to the end of the talk, I want to summarize what the basic messages are going to be. The first message is, you see, the question of this session is the universe unique? Well, in a sense, of course, if you think of the universe at all that exists, by definition, the universe has to be unique. But the key point is that what we regard as the unique universe is always growing. And as it grows, so in some sense does the domain of science. And that's one of the sort of points I want to get across. You see, one of the issues is going to be, to me, the interesting issue is not whether the multiverse exists. The issue is whether it's part of science. And this is the sort of thing that George Ellis is always arguing. I have a different view from George, but nevertheless, I think the issue is really crucial. And so the nature of science changes. Second message, the currently observable universe is a minuscule part of a larger physical reality. The multiverse is the culmination of what we might call a macro-micro connection. The history of science can be thought of as people getting to understand ever larger scales and ever smaller scales. And it's a sort of merging of these two, especially in particular through the Big Bang, that has given rise to this concept of the multiverse. And it comes really both from cosmology and particle physics. And as I said, really, it's not just a question of whether there's a multiverse. The question is really how many multiverses are there? Because there are lots and lots of proposals for how there could be a multiverse. Indeed, you can have a sort of hierarchy of multiverses. Now, the other thing is that I personally, at least, very much relate the multiverse to the fine-tunings, which are invoked in the anthropic principle. I don't like the word anthropic principle. I tend to think of it as a complexity principle, but to me it is a real puzzle. And the multiverse is not invoked in order to explain the anthropic fine-tunings. It comes out of independent developments in physics. Nevertheless, I take the view that if you've got the multiverse there, it is the most natural explanation of the fine-tunings. And then the last message I hope I'll get onto, and it really is addressed to George, and that is that the nature of legitimate science changes. The interesting question is, are such speculations scientific or not? And that's what I think is a really interesting debate. And I tend to argue it is, but only because I feel the nature of science does change. And furthermore, once you change it, I also like to think that science may eventually, for example, be able to accommodate things like mentality and first personhood, etc., which most scientists would say it can't do. Most people would say those sort of issues are nothing to do with physics. But I like to think possibly you can extend science and physics even to talk about things like mentality and the passage of time. Now, let me now start off, though, talking about the evolution of the unique universe. Now, the way I'm going to do this, I want to actually give a brief overview of the history of cosmology, essentially. Because most people aren't cosmologists, I feel part of my role is at least to give a broad introduction to the ideas of modern cosmology. But I want to do it in such a way that it will also get across certain historical lessons. So let me just, this will be very familiar to most of you, but let me just start off. Obviously, we have Homo sapiens started off with the geocentric view, in which you've got the Earth at the center. So the Earth essentially is the universe. It's the center of the universe. It is unique. And of course, the stars are just the domain of the divine, beyond science altogether. So that was the sort of Aristotelian view. That really died when Tycho Brahe was taking a walk in 1572, and I'm sure you know the story. He saw the supernova, the bright light in the sky, which was the supernova in Cassiopeia, and the important thing was this light he noticed over the subsequent 6 months, it didn't move. And therefore, as the Earth went around the sun, of course, it should have moved. And it didn't move, and therefore he knew that it had to be a long, long way away. But this clashed with the view of the time that the heavens could never change, and therefore people didn't believe him. They didn't believe this object could be at such a great distance. And he made this famous remark, crassa ingenia o coicus coeli spectoris, which means, oh, thick-wit, so blind watchers of the sky. And basically, he made that remark because he was annoyed that people would not believe the evidence of their own eyes. And they didn't, because there was this theoretical prejudice that the things in the heavens cannot change. And so that's the lesson here. Theoretical prejudice should not blind one to the evidence. And now, in the context of the multiverse debate, I think of the evidence as the fine-tunings. Then, of course, we know that that Copernicus was the person who realized at the center of it was the Earth that went around the sun, and that basically the sun, that you have the heliocentric view, in which the sun essentially is the unique universe. Even in those days, it was assumed, therefore, that the domain of science could not go beyond the solar system. I mean, Galileo realized that the sun was just one of, like all the other stars, it was just closer, but it was assumed that science will be confined to the solar system. And Auguste Comte said, never by any means will we be able to study their chemical compositions. He meant by that the stars. The field of positive philosophy lies entirely within the solar system, the study of the universe being inaccessible in any possible science. Now, of course, shortly after that, they discovered spectroscopy, so of course he was proved wrong. But the lesson you learn from that is that new observational developments are hard to anticipate. And so when you limit your definition of science, always bear that in mind. I mean, every message here is meant to have some relevance to the multiverse debate. Then, of course, we discovered that the sun is just one of hundreds of billions of stars forming the galaxy. So we now have the galactocentric view. I mean, even up to the 1920s, most people took the view that the galaxy was the universe, the unique universe. Although, of course, way back into the 18th century, people had speculated that some of the nebulae might have been extragalactic. It wasn't the mainstream view. And there was this, in fact, the word universe was so unpopular that Ernest Rutherford used to have a sign saying, don't let me hear anyone use the word universe in my department. That was in the beginning of the 20th century. Now, you won't hear that today, but you will see people who've got the word multiverse there. Don't let anyone mention the multiverse in my department. Now, there was, of course, the great debate in 1921 about whether or not some of these nebulae were outside our galaxy between Shapley, who believed that everything was basically inside the galaxy, and Curtis, who thought everything was there really were these island universes outside. That debate was resolved by Hubble, who was able to measure the distance to the Andromeda galaxy using Cepheid variables. And so that resolved that debate. And then, of course, Hubble then went on to measure not only the distances of galaxies, but he was able to measure the redshift. He was able to determine from their redshift that the galaxies were moving away from us. So there was this famous relationship between their redshift and their distance. And that's the famous Hubble's law. And there was his original data in 1929, velocity versus distance. And is this a pointer? Yes. And of course, there wasn't very much data at the time, but that was the basis of the famous Hubble law. Nowadays, of course, we have much more data going out far further, and we see that, of course, that nice linear relationship is very well satisfied. Hubble's original data was just that tiny little corner at the bottom left-hand side. And it's on the basis of that if the universe is expanding, of course, that means that if you play the picture backwards, eventually everything must be compressed, and so you start off with the Big Bang, and if you write Hubble's law just in terms of the Hubble constant, you know that the actual Hubble time, the age of the time since the Big Bang, is basically just the inverse of that constant, which, as we've heard many times, is 13.7 billion years. And as we heard from Joel, that agrees with all sorts of other measurements of the age of the universe. Now, actually, in theory, that result had already been anticipated, because in 1922, Friedman, on the basis of the equations of general relativity, had already predicted that the universe should be expanding. And he'd got all the various cosmological models which recollapse or expand forever. But unfortunately, no one noticed this. Einstein didn't believe it, and his paper was essentially neglected. And the lesson here is, don't reject a theory because there's no observational support. Einstein thought the universe was static, and therefore he said he wasn't interested in this. But of course, we know that was wrong. I want to say a word about Lemaitre, because actually Lemaitre, who, as I mentioned, we had the meeting to celebrate the 80th anniversary of his time in Cambridge, I guess, last summer. And he has a remarkable role in cosmology. He actually derived, independently of Friedman, the dynamical equations which describe the expansion of the universe. And furthermore, he got Hubble's law. And furthermore, he was aware of the data, unlike Friedman. And in fact, in principle, Lemaitre could have got the estimate of the Hubble parameter. This is only just come out this last year, but his paper was translated into English, but actually the translation didn't include this business about the Hubble constant. So the data he had available could, in principle, have predicted Hubble's constants. And if you use his data, he would have got a Hubble constant of 625 rather than the value of 530, which was obtained by Hubble himself. So it really was quite a remarkable achievement for which he doesn't normally get the credit. There is an argument that it should be Lemaitre's law rather than Hubble's law. But the other great achievement of Lemaitre in 1932 was that he realized that if you take the Hubble expansion seriously, the universe must have started with a Big Bang, with the state which he called the primeval atom. And so Lemaitre is always called the father of the Big Bang. And he made many other amazing contributions as well to cosmology. Now, how did people react to this? Einstein, reacting to Lemaitre's paper, your mass is correct, but your physics is abominable. And how did Eddington respond? Eddington was, in a sense, the protege of Lemaitre. He was the one who got his paper translated. Philosophically, the notion of a beginning of the present order of nature is repugnant to me. The reason he said that was because Eddington thought that talking about the Big Bang was too close to theology, essentially. So what do we learn from that? Well, don't be deterred by the opposition of great scientists. So just if you have a theory and all the leading people in the field tell you it's wrong, never mind. Okay. One of the really important calculations in Big Bang was to calculate the synthesis of the light elements a few minutes after the Big Bang. That was first done by Alpha and Herman. But they always said cosmology was then a skeptically regarded discipline, not worked in by sensible scientists. Most people just did not take seriously what they were doing, because at this point they hadn't discovered the microwave background. Then, of course, in 1965, the microwave background was discovered. And since then, of course, people have studied the microwave background with ever more precise instrumentations, in particular satellites. This is the famous picture from the WMAP satellite, where, of course, the color corresponds to the temperature. And studying those temperature fluctuations is what's given vital information about the history of the universe. And not only that, of course, but we've also been able to study galaxies to much, much greater distances. This is the Hubble Deep Field. Now, and so this is the sort of picture we have at the moment. We've now gone to the geocentric view. I've now got a nice picture from Joel and Nancy's book, the view from the center of the universe, which to me summarizes the cosmocentric view very nicely. The idea is that we can always regard ourselves at being at the center, and as we look out to larger distances, we're also looking back in time, of course. And so you're seeing shells of stars and of galaxies at ever larger distances. And when you're looking at the microwave background, you're essentially looking at a shell, a sphere, a spherical shell, which corresponds to something like 400,000 years after the Big Bang. So that is the picture we have. But it's an interesting thing this is a slightly more technical picture. Although it looks as though this shell is at some great distance, which it is in a certain sense, it's at the edge of the universe, actually when you're looking back to the beginning of the universe, you're actually looking back to when the universe was actually very, very small. Okay, because you're looking back to very, very large distances, means very, very early times when the universe was very, very small. And if you represent things in another way, this is what's called a conformal diagram, you can see actually you're looking back to when the universe was very small. And I won't go into the details of this diagram. If you're a relativist, you'll understand it very well. But the key point about this diagram is this, that if the universe begun at a time in the past t0, which, as I said, is about 13.7 billion years, then essentially you cannot see further than the distance light has traveled in that time. Now, as it happens, there's another factor of 3, because space itself, the expansion of space carries life along. So the size of the observable universe turns out to be something like 42 billion light years. You cannot see further than that. Now, so the message so far I've given you is that what we call the universe has changed. We started off with the geocentric view, the heliocentric view, the galactocentric view, and now we've got the cosmocentric view. But the question is, what happens beyond that particle horizon? You see, it would be crazy to say the universe ends at the particle horizon. It's like when you're on the surface on a boat up a mast, you can just see for 30 miles. You don't believe that the ocean is going to come to an end. So nobody in their right mind would say the universe ends at the particle horizon. So the question is, what is beyond it? And the crucial clue to this was connected with the cosmological constant, which Einstein first introduced into his equations in 1917, because he thought the universe was static. Remember, Einstein thought the universe was essentially just the galaxy. He didn't want an expanding universe. He introduced this repulsive term in order to balance gravity, so he had a static model. That's why he didn't believe Friedman's model, and that's why he didn't believe Lemaitre's model. When, of course, finally Hubble discovered the expansion of the universe, he realized he made a big mistake, and he called it his biggest blunder, of course. Long gap, 5 years. It took him quite a long time before he realized it. But then the irony is, as I'm sure you all know, is that in 1998, astronomers found that actually there is a cosmological constant, because after that, most people assumed the cosmological constant was 0. But that turned out that that was his biggest blunder. The biggest blunder was saying the first one was his biggest blunder. And so the crucial discovery then in 1998 was that the universe was accelerating. And that came from essentially plotting the distance redshift diagram, but just going to larger redshifts. So you'd expect the expansion of the universe to slow down, but actually it's speeding up. And the assumption is the way you do this is you measure supernovae, the same sort of supernova that Tycho Brahe had seen, which started off our story. These are the supernova which they were using. They're standard candles, so you can measure the distance because of the physics of these objects. Now, there was a bit of controversy about this. It's now accepted by the vast majority of cosmologists that this is true, and it's a profoundly important result. As you all know, just last week, the Nobel Prize was awarded to the 3 people, Perlmutter, Schmidt, and Rees, who discovered this. So it must be true. Now, what actually does it mean? What is causing this acceleration? Well, most people, the simplest assumption is that it is simply a cosmological constant. I mean, there are models where it's a scalar field rather than the cosmological constant, but to a first approximation, it's a cosmological constant. And what is the cosmological constant? In some sense, it's simply the mass density of empty space. Now, and we call it dark energy. Now, what's interesting is the same cosmological constant, which we now, the same sort of cosmological constant, which we now associate with the acceleration of the universe, cosmologists were always quite prepared to accept in the early universe. Cosmologists now always invoke inflation. It's the sort of mainstream view now, which says that the early universe went through a phase where the vacuum state dominated the energy, and it expanded exponentially. And for various reasons, inflation solves all of the various problems, some of the problems of cosmology. So now here is the summary of the picture of the Big Bang, which most cosmologists have now. We're plotting against time, basically the history of the universe. So we start off at the Big Bang itself, which is where the quantum gravity epoch. You have this inflation. Then after about 400,000 years, you've got the radiation decoupled, so that's what you see in the microwave background. And then you have the period, it's the dark ages, and then galaxies form, and then stars and planets and people form, and then satellites form, and there's WMAP. I have, of course, to update this, that's Planck, that's the European one, which is currently getting data. So that's our summary view of modern cosmology. And so what is the future universe? Well, if it's the simplest picture now is that the universe would carry on accelerating forever. If it's a simple cosmological constant, the universe would carry on expanding forever. And the remarkable thing is Lemaitre, the same Lemaitre who first predicted the Big Bang, he was the person who first produced the models with the cosmological constant which predicted this behavior. So the title of my talk was Lemaitre's Prescience, because he got both the beginning and the end of the universe, which is pretty good. Now, but then the question is, this picture here is the visible universe, okay? What lies beyond it? Now, and the crucial point is this, that in the inflationary picture, that our universe, the observable universe, is just this little pink patch here, is part of a larger physical reality. Now, what I mean by that is, first of all, it's part of some bubble. This is in the inflationary picture. I'm being rather dogmatic about this. I don't know. I'm just saying what the simplest models are. So in the simplest model, our universe is part of the bubble. You know, in other words, to use the boat on the ocean analogy, this is the Atlantic Ocean or whatever. But then the same inflationary theories, which say we're in a bubble, predict there are other bubbles. And so in this picture, this is the sort of image you would have, that all of these are basically different universes. You can call them different universes. Now, I've talked about cosmology so far, which is in some sense the exploration to ever larger and larger scales. But now let me talk about the study of particle physics. One of the great triumphs of particle physics is to understand that all the various forces are unified in a single theory. And so I'm sure you're all familiar with this. Electricity and magnetism were unified by Maxwell and Faraday into the electromagnetic force. Then in the 1970s, it was realized that the electromagnetic force and the weak force can be combined as part of the electroweak force, which has been experimentally confirmed, and they got the Nobel Prize, so that must be true. Theorists realized that the strong force could be unified with the electroweak force as part of the grand unification, still not experimentally verified, but nevertheless thought to be true. At least one can speculate what its predictions are. But of course the real triumph is the real dream is to unify these forces with gravity. And as I'm sure you know, the leading contender at the moment is M-theory. So which is the idea that strings are fundamental rather than point particles. And so that's the great triumph, one of the great triumphs of particle physics, is to show that all the forces of nature and all the fundamental constituents of matter are all married together in this beautiful picture. But this picture comes at a price, in the sense that it's quite a long way from our normal everyday reality. The thing about M-theory is that it invokes these extra dimensions. So here's the normal 4 dimensions of space and time, which we all believe in, apart from Julian. But then, of course, you have 5 dimensions, which is in Kaluza-Klein's attempt to explain electricity in electromagnetic interactions geometrically. You invoke a 5th dimension. Ordinary superstring theory had 10 dimensions. And then M-theory, essentially there were 5 different types of superstring theory, and M-theory marries them all together in an 11-dimensional theory. And so the picture of M-theory is that the picture on the front of my book, for example, it's the Clauber-Yau space, which sort of describes the geometry of these extra dimensions. And one particular aspect of M-theory is that you're describing the vacuum states. And originally, it was hoped that string theory would give us a unique vacuum state, which would mean that all the constants of physics were determined. But now it seems as though there are many, many, huge number of these vacuum states. And this is what's called the string landscape scenario. And the thing about a string landscape is that it has a cosmological constant. Okay? The vacuum corresponds to a cosmological constant. So this is where it's linking up with the first picture. So what we've got from particle physics there, from physics, is that we've really got paradigm shifts of increasing dimensionality. Because the point I should make is that these extra dimensions are normally compactified. That's to say they're wrapped up on the scale of the Planck length, so you don't see them. And this is the sort of normal view. If you, for example, take the 5th dimension, if you look up close, it's closed on the scale of the Planck length, say. But if you stand a little way back, but you are, you don't see it, it just looks like a hose pipe. So that's the normal idea of a compactified extra dimension. And so the history of physics, in some sense, is a history of paradigms with increasing dimensionality. So we've got the Newton picture, Einstein's 4-dimensional picture, Kaluza-Klein's 5-dimensional picture, superstrings are 10-dimensional, M-theory is 11-dimensional. I was quite interested in what Julian said yesterday about one of the great contributions of the Greeks was to realize there was a 3rd dimension. So that fits into that rather nicely. But something rather interesting is that although it's normally assumed those dimensions are compactified, there's a particularly popular model at the moment associated with Randall and Sundrum, which says that the 11th dimension may actually be extended. And in this picture, it's called brane cosmology. Our world, our physical world, our space-time, is a brane, B-R-A-N-E, not to be confused with the B-R-A-I-N-E, sorry, B-R-A-I-N, or the Boltzmann branes, which I think Tim's going to talk about. And you think of this brane as being in this 5-dimensional bulk. And I like this picture, so bear that in mind. Now, but the point I'm trying to make is that we've come from two directions. We come from the cosmology direction and the particle physics direction. And they've all said the same, they both said the same thing. Basically, cosmology tells us that there has to be inflation and acceleration. Particle physics tells us, M theory, that we've got this string landscape scenario. And the common message is the vacuum energy. They both seem to require a cosmological constant. And, but there is a puzzle about this cosmological constant, and that is that it's 120 orders of magnitude smaller than you would naively expect. If you take the Planck scale, which is 10 to the minus 33 centimeters, it corresponds to a cosmological constant in appropriate units of 10 to the 66. The actual density associated with the cosmological constant, the dark energy, is 10 to the minus 56 centimeters to the minus 2. So there's a discrepancy there of 122. And that's a really big fine-tuning problem. Now, why? Now then, one of the things Weinberg realized in '87 was that actually galaxies couldn't form if the cosmological constant was too large, because it's a repulsive force which stops galaxies forming. So he says that he pointed out that the density of the density associated with the vacuum, this is in the units of the critical density, has to be less than about 0.6. He said that is a constraint required for us to be here. Okay, so that's going to play an important role. He's saying there's no physical reason why it should be as small as it is, but there's a selection effect. Namely, if we're going to be here in galaxies, it better be that small. Now then, I want to summarize the picture so far. This is my favorite diagram. It's one that Martin shows as well, Martin Rees shows. It's the Ouroboros. And there are many different versions of the Ouroboros. This is my favorite one. And I'm saying that not just because Joel and Nancy are in the audience. It's very, I mean, it's beautiful. The point about the Ouroboros, it's the snake swallowing its own tail, and you have all the different scales of structure in the universe around it. So you have men and women at the bottom, and you go up to ever larger scales, mountains, planets, stars, galaxies, the whole visible universe on this side. On this side you have things like ants and amoeba and atoms and nuclei and all these atomic nuclei, and then all the quarks and all the dark matter, and you end up with the Planck scale. So basically this is to me, this is, it encapsulates the triumph of physics in understanding the links between the macroscopic and the microscopic worlds. It also represents the fact that you've got these links between the macro and micro world. I mean, electricity links an atom to a solid object because the same electric force which keeps an electron in orbit around a proton is what basically determines the structure of a solid. The weak-strong force, the same weak-strong force which hold the nuclei together and are responsible for nuclear decay in atoms, are also what's responsible for the burning of nuclear fuel in a star. The same electroweak force which is associated with the dark matter associated with galaxies is maybe associated with the dark matter particles, the WIMPs. The grain unified force, which is associated with very high energy in particle physics, may be responsible for the sort of inflation and the density perturbations and things like that. So to me, this is a beautiful diagram. And it's because it basically embodies all of our knowledge of physics. And it represents the triumph of physics. And then, but the point I want to make is that up at the top, the multiverse and M theory are they just represent the culmination of this process. And in particular, I highlighted higher dimensions here because I think they play a role. So the message at this point, the Big Bang in some sense is the culmination of this macro-micro connection. Because the point is, what happens when the snake, why does the head meet the tail? Well, that's because when you look out to the largest distances, you're looking back in time to when the universe was smaller, it is smaller and smaller. And so that is why, in some sense, this beautiful paradox that the very large merges with the very small. Now, I should say, I focus so far on really one particular multiverse scenario. The multiverse scenario associated with the string landscape, because I do think that really is the significance of this cosmological constant. That's what got the particle physicists interested in multiverse. Cosmologists have been interested in it for quite a long time. It was the links with the cosmological constant and the vacuum which really got the particle physicists involved. But I should say there are many other scenarios for the multiverse. One of the oldest ones is the cyclic universe, the idea of the universe which expands and bounces. And you can imagine that every time it bounces, maybe, you know, we don't really understand the bounce, but maybe quantum gravity does it. And we can imagine the constants of physics changing as it does it. So that's, if you like, a lot of universes strung out in time. This is the eternal inflation. Is a variance of inflation in which these bubbles are forming in time and space in some sense. So this is a picture of eternal inflation, associated in particular with Vilenkin and Linda, the most popular version of inflation at the moment. We don't know it took place, but it's just that it seems to happen in many particular models. I mean, George will be the first person to say that we don't know it's true, so it is just a model. But nevertheless, it is the model which seems to be attracting interest. You get some beautiful pictures here. Just from an artistic point of view, these are other representations of eternal inflation. Here are some other multiverse scenarios. I mentioned in the brain scenario that our world is a brain, a four-dimensional sheet in a higher-dimensional bulk. In principle, you could have other brains. And so you could have many worlds spread out in this fifth dimension. You know, they're just up there, well, or somewhere. And indeed, in some pictures, the collision of those brains is what's responsible for the Big Bang. This is the many worlds interpretation of quantum mechanics. I'm not going to talk about that in great detail, but you know the idea is that the universe is described by a wave function, and that when you make an observation, you collapse the wave function, but the universe splits into parallel worlds according to how it actually collapses. But that was, in some sense, the oldest version of the multiverse. And then there's quantum cosmology. The question is, what happens when you get to the Big Bang? Obviously, classical relativity breaks down, and you need a merger of quantum theory and relativity, which is what quantum cosmology does. But the remarkable thing is that quantum cosmologists are able also to have a picture. They produce another version of the multiverse, which says that in some sense you imagine all possible histories of the universe being superposed. And so that's quantum cosmology. So basically, just to summarize these multiverse scenarios, some of them have come from cosmology, like the cyclic model, eternal inflation, colliding brains. Some of them come from particle physics, like the quantum many worlds, string landscape, and quantum cosmology. But the message is, cosmology and particle physics suggest there could be many other universes. And so, as I said, it's not just a question of whether you believe in the multiverse. The question is, how many of them are you going to believe in? I'll miss out this. Let me just summarize what Tegmark gives a nice overview, a classification. And this is basically what he calls level 1 of the different Hubble volumes. They're just beyond the visible horizon size. Priya referred to this on the first day. Level 2 is just the different inflationary bubbles. In fact, any scenario which is producing lots of big bangs, separate big bangs, would be described as level 2. Level 3 is associated with the quantum the parallel worlds in quantum theory. Level 4 is even more speculative. It's different mathematical structures, and the idea here is anything which can exist mathematically will exist physically somewhere, but I'm not a great advocate of that. So, the key features, where are the parallel universes? These ones are just far away in space. These are sort of almost infinitely far away. This is a bubble picture. This exists in Hilbert space. This is some mathematical space. And what are the four multiverses like? Level 1 all have the same laws. Level 2, the laws may be different in these different bubbles, so you've got effective bylaws. Tegmark argued there's nothing qualitatively new in the parallel universe thing, as Priya mentioned. It's just in a different space. And of course, not only the laws, but all the equations could be different in level 4. Now, so here is this picture of the, going back to this beautiful picture of the Ouroboros. And we've seen how the multiverse in particular now comes out of that very naturally. However, for this, all the triumph of physics, there's something rather sad about this. We have become, as human Homo sapiens, we seem to have become very insignificant. Here is a famous Snoopy cartoon. Did I get it from you anyway? Whichever. You are of no importance, did you know that? You are only the tiniest speck in an enormous universe. Then I might as well go back to sleep. I hope you haven't, but anyway. And in a way, this is summarized by Weinberg. The more the universe seems comprehensible, the more it seems pointless. And that's rather depressing. However, there has grown up a reaction against this, which I'm going to go through. It's associated with the anthropic, the fine-tunings, which I wanted to... Priya, when did I start?
3 seconds.
How long have I got? Sorry?
10 minutes.
10 minutes, okay. Now, let's go back to... I started off with the anthropocentric, geocentric view in which man is central. We all know that was actually destroyed by Newton's mechanistic view, which says that basically the universe exists independent of our awareness. So man and mind are basically irrelevant, which is a bit depressing. But then, of course, the reaction came from the anthropic view, which says that certain features of the universe are explained by the requirement that we should be here asking questions about it. Anthropos comes from the Greek word for man. It's a rather, I don't like the word anthropos because it's really nothing to do with Homo sapiens in particular. It's really just saying the universe has to allow complexity to arise. So I prefer to think of it as the complexity principle. The Big Bang should lead to increasing order and complexity, and then mind just becomes one particular aspect of that. Now, there is a huge literature on this, and I can't really go through it in detail, especially since I'm running out of time, but let me just give you a few examples. I talked about the 4 forces, and the 4 forces have got a certain strength described by a coupling constant. Now, for the gravitational, for the force between 2 protons, it's alpha g, and it's 10 to the minus 40. For the weak force, it's 10 to the minus 10. For the electric force, it's 10 to the minus 2. It's actually 1 over 137. For the strong force, it's about 10. So these are just dimensionless numbers which describe the strength of the forces. Now, I told you how physicists have been remarkably successful in unifying all the forces, but they can't actually explain what these coupling constants are. And so the question is, will the final theory of physics explain these values? And of course, most physicists would like the answer to be yes. However, it doesn't look like that. If I actually plot my Ouroboros diagram again, these scales actually, what they actually depend on, they depend on the value of alpha g, which you remember is 10 to the minus 40. And actually, the scales go all the way from 1, all the way to alpha g to the minus 3/4, all the way up to alpha g to the minus 3/2. That's actually the scale of the physical universe, if you work it out in units of the Planck length. Notice that's why Homo sapiens are right down in the middle. They are the geometric mean of the Planck scale and the size of the universe. But the question is, what would happen if alpha g was different? If alpha g was different, this diagram would look the same, but it would expand. The scale would change. So why does alpha g have that value? Well, the fact is that there are various fine-tunings which seem to be required. And I'm not going to go into the physics of these because I'm running out of time. But for example, one thing you require is that alpha g should be the 20th power of alpha e, in order that that you have both stars which are convective and radiative. You need both types of stars. The convective stars are associated with the radiative stars are associated with supernova. The convective stars may be associated with planetary systems for various reasons. Now that is a coincidence which is satisfied. The 20th power of 10 to the minus 2 is 10 to the minus 40. And it's required anthropically, but nobody in physics doesn't explain it. Likewise, supernova, I started off with the picture of a supernova. What causes a supernova? It's basically it collapses and the neutrinos get generated and then they blow off the envelope of the star through weak interactions. That only happens because alpha G is the fourth power of alpha W. Again, it's true. The fourth power of 10 to the minus 10 is 10 to the minus 40. But nobody can explain it. I mean, physicists cannot explain why that relationship should be true. It just happens to be necessary. If the weak interaction was too weak, the neutrinos would just flow through the surface of the star and they wouldn't explode. If it was too strong, the neutrinos would never even get outside the core. And so the point is that there's these relationships are required for life but can't be explained. And physics is full of these sorts of fine-tunings. I'm not going to go through them. There's the famous triple alpha coincidence. Tegmark has summarized some of the anthropic relationships between the value of the strong coupling constant and the electromagnetic constant. I'm not going to go through these in detail. There's a famous book by Martin Rees called Just Six Numbers, where he summarizes these the various cosmological parameters which seem to be fine-tuned. One of them is a ratio of alpha G to alpha, but others is the strength of the nuclear binding, the matter density, the cosmological density, the scale of the density fluctuations, even the number of dimensions. So there are all sorts of things which have to be explained. Now I'm going to go through the next slides very quickly because I'm running out of time. This was just, all right, this is just to give you the anthropic principle has created tremendous controversy. People get very emotional about it. Here's some quotes by Freeman Dyson. I do not feel like an alien in this universe. The more I examine the universe and examine the details of its architecture, the more evidence I find that the universe in some sense must have known we were coming. Okay, so he's in favor. But then, Heinz Pajos, the influence of the anthropic principle on contemporary cosmological models has been sterile. It has explained nothing and it has even had a negative influence. I would opt for rejecting the anthropic principle as needless clutter in the conceptual repertoire of science. Strongly opposed. And they represent two camps. But maybe the best way, the more balanced view is Brandon Carter, who coined the phrase anthropic. The anthropic principle is a middle ground between the primitive anthropocentrism of the pre-Copernican age and the equally unjustifiable antithesis that no place or time in the universe can be privileged in any way. And that, I think, is the view now, which is my own view, and it's the view, I think, which is now becoming more popular. Now, but as I said, the key thing, to my mind, about the anthropic fine-tunings is that they are what allow the build-up of complexity during the Big Bang. So we start off just with quarks, which go into nucleons and atoms and simple molecules, biomolecules, cells, organisms. This is time measured from the Big Bang. This is called a pyramid of complexity. That pyramid of complexity can only arise because of the fine-tunings. Now, okay, so now I just want to end up by talking about the interpretations of the fine-tunings. Obviously, for people of a theological disposition, it's quite tempting to argue that maybe God created the universe, and that you imagine this is like a space of all the coupling constants, and God simply put his pin in at the place where life can arise. Now, most physicists naturally don't like that. There are other views. This is the sort of Wheeler view that in some sense you start off with the Big Bang and it evolves through complexity towards to brains and consciousness, and the brains then contemplate the origin of the universe and sort of get a closed loop like that. So this is based on the idea that consciousness collapses the wave function. But again, a rather mystical perspective. But the point about the anthropic, the multiverse view, is that if you've got lots of universes in which you've got all the different constants, it's fairly natural to say, well, then we simply live in one of the universes where the constants have the values required for us to be here. And many physicists regard this as much more satisfactory than invoking God. I mean, essentially, I like the analogy. If you buy a lottery ticket and you win the lottery, and you win $100 million, whatever it is, you think, wow, that's amazing. But then you don't think it's so amazing when you realize that actually 100 million people, what it was, also bought lottery tickets. If you were the only person who bought a lottery ticket, you will be pretty surprised, okay? But you're not surprised because many other people did. And it's
still surprised.
Well, it's still surprised, okay, but I mean, I've never had the experience. But in any case, in any case, that's the basic idea. If you've got lots of universes, it doesn't matter how low the probability of having the right constants, they will be there somewhere. And I'm not invoking, incidentally, an infinity of universes. I share George's discomfort with infinities. And basically, all the multiverse scenarios are saying is if you've got a model for making a big bang, okay, whatever your model is, it's going to make other big bangs, okay? You've got a machine for generating big bangs. This is generating universes. I have to say, I got this from, this is Paul Davis's picture, by the way. But now the question is, do we believe this? And really, here's my favorite picture of Einstein in a dressing gown. What really interests me is whether God had any choice in the creation of the world. Because the fundamental question is this: will the fundamental theory tell us what the constants of nature are? This comes from Martin. Martin's not here? Right, okay. This comes from Martin. And if the fundamental theory is going to determine all the parameters uniquely, which is what some people like, then of course there would never be any role for anthropic reasoning. If, on the other hand, you can allow that there are different universes which allow different parameters, different initial conditions, different types of symmetry breaking, different compactification of these extra dimensions, in that case it's very natural to say that you have got these multiverses, some of which will be anthropically allowed. And so that's the fundamental question. However, the debate is this. Oh no. The debate is this. Is it science? Because the point about this is that you can't see the other universes. And myself and George have regular little banters about this. We wrote an article in Astronomy and Geophysics, and here are some quotes from George. I'm sure he's quoted himself in his talk yesterday. The multiverse theory cannot make any testable predictions because it can explain anything at all. Can one maintain one has a genuine scientific theory when direct and indeed indirect tests of the theory are impossible? I take the view, I agree you need falsifiability, but to me the question is how long do you have to wait? And I'm prepared to wait longer than George, okay? Basically. I mean, the point is this: it's true you can't see these other universes, but the point is, if the theories which predict the multiverse can themselves be tested, you then have got indirect evidence. And so if, for example, you can show that M theory is true in the Large Hadron Collider, then you have a reason to believe in the multiverse. After all, there are many things which aren't, you can never test every prediction of a theory. You know, you can't look at a free quark by definition, but that doesn't mean you don't think QCD is proper physics. You can't look inside a black hole by definition, but that doesn't mean you don't think that black holes aren't proper physics. We accept that not all aspects of a theory have to be observable. The question is, how much of a theory has to be testable before you believe it? And it's not a definite yes or no, it's a grey area. Of course, the problem is that some people argue that M theory itself is not science. Some people argue that it's mathematics, not physics, because it can't be tested. And that's really what George is saying. And I'm saying, well, we just have to wait longer before we can test it. And the point is, when we ask about the nature of legitimate science, I'm sorry, Priya, when we ask about the nature, we got this process of you have an idea, it makes predictions, you have observations which either confirm or disconfirm, and then leads to further predictions. That is the nature of science. But to me, the crucial question is, what is the time scale of the process? Now, people say M theory after 20 years has not solved its problems. It's dead loss, okay? Well, to me, that's absurd. You know, it might take 100 years. It's a complicated theory. Why should we think that all our theories have to be solved on the timescale of a PhD thesis? I mean, you know, it may take 100 years to solve the problems of M theory, but I don't think you should say that means it's not science, okay, just because it takes 100 years. And the question is, there could in principle be evidence for these other universes. I mean, I must finish now in 1 minute. I mean, for example, no, I'm not going to go. Let me just say that there is conceivable evidence for these other universes. One of the best, I think the most topical evidence comes from the possibility that there are other bubbles which may have collided with our bubble at an early phase, that there may be signatures in the microwave sky of collisions with other universes. And that is, to me, an example of how you might get direct evidence for these other universes. So I don't think it's clear that, sorry, I'm going through that very quickly, I'm about to end. So my final message is this, that the nature of legitimate science does actually change. And this is a quote from the book from Steven Weinberg. We usually mark advances in the history of science by what we learn about nature, but at certain critical moments, the most important thing is what we discover about science itself. These discoveries lead to changes in how we score our work in what we consider to be an acceptable theory. And if we ask what are the various features of science, in the history of science, you remember I started off going through the history of cosmology, you might assume experiments are crucial to science, but actually you can't do experiments in astronomy. You can't experiment with stars and galaxies, but in some sense nature does its experiments for you because you can see all the millions of stars and the galaxies. So you don't need to do experiments. The cosmology is a bit more difficult because we've only got one universe, so you might think, well, that's not part of science, but we still can do science because we get all this implicit data. And then there's the problem of testability. Well, it is true that you can't directly look at these other universes, but I've already argued that there is maybe indirect ways of testing things. And so my view is that in some sense, what you regard as there's a process in which metaphysics evolves into questions which are metaphysical become physical, ideas which are regarded as metacosmology become genuine cosmology. So I'm sorry I've gone on a little bit longer than I expected to, but the point I'm trying to make is personally I think that the multiverse is there. It may not be science in the way we understand science at the moment, but I do think in principle it should be regarded as legitimate science. Thank you. So I should finish now. Okay. Okay. So I'm going to close here. Sorry, I overshot. Yeah.
No,
It's loaded already. Oh, okay.
Sorry, I can just stop this here.
You can leave it for now, actually.
Yeah, okay.
The podium doesn't let you leave, huh? Okay.
Thank you.
Thank you so much, Bernard. So we're moving on to the second presentation in this session. And I'm very happy to introduce Tim Maudlin, who's a professor in the Department of Philosophy at NYU. Quite recently, was at Rutgers. His areas of research include philosophy of science, philosophy of physics, and metaphysics. He's the author of several books, Quantum Non-Locality and Relativity, Metaphysical Intimations of Modern Physics. My personal favorite is one titled Truth and Paradox. And he has an upcoming book, Philosophy of Physics, Space and Time. I think it's Princeton University Press next year. So, Tim?
So
let me start by just connecting a bit of what I'm going to say to the beginnings and the endings of Bernard's talk, and I'm going to take for granted you could absorb some stuff that went by very quickly. So there were some morals at the beginning of the talk, and the morals sort of tended to seem to have the theme, don't worry, right? Don't worry if there's no observational evidence for your theory. Don't worry if all the experts think it's crazy. Well, you got to worry sometime, right? There does come a time for worry, and I guess toward the end, there's sometimes I think maybe a terminological question that isn't of much interest. Is it science? I find sometimes that's a bit like people arguing, is it art? As if declaring something to be art gives it a free pass, right? Often when I hear these discussions, I think, yeah, it's art. It's just really bad art, right? So there's some scientific project, and part of the scientific project is obviously inventing theories, thinking up new ideas, trying to make them clear, trying to derive whatever you can from them. And at some point, there's another part which is trying to find evidence to believe that they're correct. And what I want to worry about here is just that last part in the context of the multiverse kind of scenario. And in particular, I'm just going to focus on the issue of what this idea of multiplicity, or there being a multiverse, how that affects the situation with respect to what you can think of as evidence for or against the theory. And I don't have a moral here. I actually think the arguments are very puzzling. And these are, by the way, as you'll see, these arguments actually predate all of string theory and all the multiverse stuff. As we'll see, this argument goes really, as far as I know, clearly back to Boltzmann and statistical mechanics. So there'll be a lot of connection to some things that David said. Okay, so this is now just going to be a quick review. What do we mean by saying that there's a multiverse? Well, by definition, the universe, I take it, is everything there is. So by definition, there's only one of it. That's simple, right? But it could be that everything we can, in any straightforward way, observe is only a very, very, very tiny part of all that there is physically, and that there are all these different regions that are in some sense analogous to the part we can see. That's a possibility. It might not be, right? If that possibility obtains, you then get three connected questions. What sort of physical structure would the other parts have, the parts we can't directly see? Why is it that the other parts are not directly observable? And given that they're not directly observable, and this is sort of the key question I want to focus on, why should we believe that they exist at all? Now, it is particularly relevant, as we know, in this context about the fine-tuning issue. So I just want to, again, mark this. So one of the main interests is that theories that postulate some kind of big multiplicity, and we'll talk for a minute what kind it has to be, they allow for a wider scope for chance. And in a way, maybe most of this talk is what that means. What does it mean to say a wider scope for chance, a wider scope for saying something only happened by chance and therefore needs no further explanation, has none and actually doesn't require further explanation. If each of the various regions in this multiplicity is a member of some large sample space, by which I mean there are just lots of ways they could have been, or imagine you're throwing dice and you say, well, the sample space is just all the different combinations that could come up. Then you'd think, just offhand, if there are lots of them, it becomes more likely that at least one region with a given set of characteristics exists, provided that those characteristics are at least represented in the sample space, right? If there are a way things could have been. So if there are many, many, many planets, then it becomes more likely that there exists a planet with any given physically possible structure. So that seems pretty intuitive, right? Even if the characteristics you're interested in are in some sense very rare or unusual in the sample space, enough multiplicity would still lead one to expect the existence of some regions with the characteristics. This is actually, the example about the lottery, the right way to put it, I take it, is this. It's not that I win that's surprising. If only one person bought a ticket and there were 100 million tickets, and that person won, whether it was me or not, that would be surprising. If there are 100 million tickets and 100 million people bought tickets and every ticket was bought, it's not surprising that somebody won, right? Which characteristics? What are we worried about here? Well, current physical theory has in it many independent degrees of freedom when you specify the physics of some observable region. And by these independent degrees of freedom, these are just sort of numbers or that we have to put into the theory by hand, if you will. And these come in sort of two classes. It's worthwhile to keep these two classes in mind. The most mundane level is what we normally call the initial conditions. So if you think if you think of the universe as being made of particles, how many did you start with? How were they? What was their original configuration? How were they moving initially? That could be lots of different possibilities. Also, and this is really key for this discussion, what we call the constants of nature, you can regard them as having been chosen from a larger space of possible values that they could have. And this was exactly what Bernard did at the end. If you look at that and you sort of try and pick out which regions in that space would allow for, and now you have to put something in, stars to form, galaxies to form, volcanoes. We tend to focus on people, but people aren't really very special in this regard. I mean, there's all kinds of, and this is the point, there are all kinds of complex structures that seem to be very sensitive to these values. We happen to be complex structures. That doesn't make us special, right? Lots of things you could pick out. I mean, you could pick out earthworms, right? You could ask, what is the world, what does the universe have to be like for there to be earthworms? Presumably, you wouldn't want to come to the conclusion that the entire universe exists for earthworms. But the argument's just as good. So if you notice that out of this space of possible values these things could take, only very few lead to this result, right? You might say, well, then it's in some sense, very improbable that we should think of the world as just having happened to have, started with these. And we might think what we need is another principle. We need something more. We want to restrict these degrees of freedom. We want to restrict the possibilities so that it doesn't look so odd. That's the intuition. I think, what I'm trying to do is just get clear about what the intuition is and how we can deal with it. Now, there's another possibility, one that isn't mentioned here. You could imagine physics advancing in a certain way in which the constants are not really independent with each other, right? You have a deeper theory that just in the theory itself relates these constants to one another in some mathematically well-defined way, and suppose the theory is somehow very simple, and it actually just has as a consequence that this one will be so much times that one, right? So at the beginning of this, you have to have the idea that these are somehow free choices that are being made independent of each other. Physics might not do that. There's another thing that could happen is you can get kind of homeostatic dynamics. That is, you can have a dynamics that will tend to drive a system toward a certain end state more or less independently of where it began. And in fact, the original inflationary scenario in cosmology was like that to solve the problem of why the universe we see around us is pretty nearly flat, which seemed to require a lot of fine-tuning. You said, well, if I add this extra dynamical bit that inflates it very quickly at the beginning, I don't need to twiddle the initial state so finely. I'm going to set aside, but you might imagine physics going on in a way to say that, gee, the things we call constants aren't really constants, they evolve, and here's the dynamics of how they evolve, and look, they will tend to be driven to certain values. I'm going to set that aside. This is not real, but this is a possibility of explaining this thing. Now, there are different kinds of multiplicity. Again, we had this just now. But we ought to make some distinctions here, particularly the ones that yield a multiplicity of values for these constants of nature. For example, the fine structure constant. I mean, he had the numbers up there you saw recently. Some kinds of multiplicity give you varieties for that. Some kinds don't. For example, and this was, again, in the third level, you saw it, those that don't are the kinds that the multiplicity is merely that there are lots of regions of space-time that are far from one another, not in direct causal contact with one another. and the kind of variety you get in the many worlds interpretation. The world may be splitting in the many world interpretation, but the fine structure constant has the same value in every one of those branches. So those, although they have a kind of multiplicity, don't have the right kind to be of relevance to the fine-tuning arguments. The ones that do, that we now people talk about, tend to rely on string theory and the string landscape, and the idea is somehow there are all these different ways that these little compactified dimensions could be topologically. Depending upon how they are, and maybe on some other details, you'll get different values for these things we call the constants of nature. And then you have some story about the production of regions of the universe in which these spaces form independently of each other and can form in all different kinds of ways, right? That's obviously the kind of multiplicity we care about here. Now, you can ask yourself, I say there are many reasons. Many regions? What isolates them from one another? All right. Well, the idea was they're somehow observationally isolated from one another. Why is that? What brings that about? Again, different of these scenarios, there are different mechanisms. It's just, again, a little bit important to think about what they are. One is straightforward spatiotemporal separation. They're just so far away from us that we can't see them. Okay? This is a sort of level 1 multiverse. Things that are outside our past light cone, we can't see. That kind of isolation, obviously, by itself does not suggest variety in any constants. It would in initial conditions, right? So if you thought, well, is there a planet with such and such characteristics, you know, a certain mass and a certain number of mountains on it or whatever, you would say, well, if there's just a lot more space out there with the same physics as we have and a lot more planets have formed, it's all the more likely that for whatever particular description you give, there's at least one of them out there that's like that. The second thing that will lead to observational isolation is what I call a causal bottleneck. Now, this is an important thing. A bottleneck is a difficulty, but not an impossibility. And you'll see why in a second that's important. So, for example, if there was some earlier epoch before our Big Bang, that earlier epoch, at least unless you really change the entire space-time structure in a very radical way, at least you could imagine that that earlier epoch could, in a fairly straightforward way, lie to our past. Right? It's just our part of the universe sort of gets smaller and smaller and denser and hotter, and then you get to something, and then if you keep going backward, you would get to something else that preceded that. But because it went through this very dense, hot phase, it's going to be hard to get information through there, right, from before to after. Just as if I, burn your house down really thoroughly, it's going to be hard to sift through the ashes and figure out what was in before I did that. Okay, but notice that's just a matter of degree, right? That's not some kind of physical impossibility. So the idea, one of the ideas in these kind of bottlenecks is, again, that the region can become so extreme in some way in temperature or whatever, that's where the constants of nature themselves could change. That's where you could get a change from one of these vacua to another. Okay. An example of this is the cyclical cosmology you saw quickly at the end, where you have a kind of Big Bang, and then somehow each Big Bang either comes back together, or Roger Penrose has a recent idea, anyway, that eventually gives rise to yet another one and yet another one, just in linear sequence. Okay. But these are in a straightforward causal sequence. One, the story is, one just gives rise, I'm assuming a general straightforward direction of time here, one gives rise to the next, gives rise to the next, and through that intermediate period, still there may be some information, there may be some causal influence there. The third kind of isolation is what I call causal transparency. This is what happens in the many world scenario. You say there are all these worlds right here in the room, right? Right now we're dividing off and there are billions more branches, and every possible thing I could be saying and doing and dancing and everything else, somebody's doing somewhere right here. And you say, well, why don't I see all that interesting stuff going on? Well, because in some technical sense, we're out of phase or we're decohered, and so we don't causally interact with each other. Notice that also, that kind of causal transparency can be a matter of degree. In fact, it's important in a way, in one way of thinking of the many worlds interpretation, that it's only a matter of degree because you want to say there are influences of the other branches, right? There are interference effects and this and that, and in the case of these brains that are stacked up very near each other in space, but you're not aware that they're there, it's not complete causal isolation. It's some very attenuated causal isolation. What that means is that in this case, you could have a signature. You could have a really observable signature in this universe of the direct influence of these other universes on what we're seeing here, right? So what are the morals just by this little taxonomy? First of all, in the cases where they're separated by causal bottlenecks and by causal transparency, since that's a matter of degree, it's possible that you could have really, in a way, straightforward or more or less straightforward observational evidence of these hidden things. And we have already what we would now consider to be straightforward observational evidence of other stuff in our universe, which is very, very causally inert. Not perfectly, but neutrinos just don't interact with much. You know, and dark matter presumably doesn't even interact that much. But it interacts a little bit, and if you're careful and you look for it, you can have really straightforward evidence that these things are there. There is a caveat about this, I should say, which is that even if you see these causal effects of something, you have to be careful whether you want to call the thing a parallel universe or another world or something. I'm saying this particularly for people who know the many worlds interpretation. So David Deutsch, whenever he talks about this, says basically we have direct observational evidence of these many worlds of quantum mechanics whenever we do a two-slit interference experiment. But in most interpretations of quantum mechanics will give you exactly the same prediction. They'll predict the interference, but they don't have these other worlds. Okay? So it tells you there's something going on, right? The interference tells you there's something going on. It doesn't necessarily tell you what's going on is exactly what Deutsch tells you is going on. So you need to be a little careful. So there are going to be possible kinds of what I would call standard evidence for a multiverse view. Strongest evidence would be direct observation of properties that are best explained as effects of the other worlds. Right? So this is the idea, again, in a cyclical cosmology where there was an earlier epoch and then it went through before our Big Bang, then our Big Bang in some sense grew out of it. People have suggested that if you look carefully at the background radiation in our world, you'll, as it were, see the causal imprint of that earlier situation. That's just straightforward evidence. That's kind of straightforward evidence we would accept as anything, right? But there can be other reasons besides that to believe, I think, that would make it plausible that there are these other worlds. And again, this is just to repeat what was said. One is that the other worlds is a logical consequence of some theory, for example, string theory, that we have direct experimental evidence in favor of, right? So I can't directly see the other worlds, but I have experiments which really seem well predicted and well explained by string theory, and I analyze string theory and I say, gee, string theory implies in its nature that these other worlds exist. So that's it's a second-hand evidential situation, but still a very strong one. In this case, I think the notice in these cases, I'm not appealing to the multiplicity itself as evidence, or to any explanatory power of the multiplicity as evidence. I'm accepting the theories on other grounds and noticing they happen to imply multiplicity. So the people I talk to, or at least the people I've talked to recently, like Sean Carroll, when I ask him, what's your view? Why should I believe in these things, in some kind of multiplicity? He will cite things like, he'll say, these are the kinds of reasons I think. He would say, I'm personally not putting a lot of weight on fine-tuning, okay? And So you have to talk to individuals who actually believe these scenarios, why they believe them, or what grounds they think you could have. Some people might quite reasonably say, look, I don't actually believe it. I think it's possible, and I think this is the kind of evidence we should look for, and these are the situations, if we got this evidence, that I think you ought to believe it. But my job here, as I see it, is actually to talk about the fine-tuning and multiplicity part. So this was all sort of setting aside much more straightforward evidential situation. Now, it is true, and George may say this, in many cases, I would have to rely on thinking the theory is correct in very extreme circumstances, right? Taking it seriously. If I check string theory and it works in the lab, and I say, but gee, it implies that in these very extreme circumstances, such and such will happen, I have to say, my reasons for believe it in this regime where I've tested it are good enough to trust it through these other regimes. Okay, so that's an interesting issue to talk about, but you'd have to go into specific details there. So let's talk about the evidential situation when we have multiplicity. So let's set that aside. On the one hand, and you see the tension here, there's the idea that merely having multiplicity, or at least multiplicity of the right kind, provides a theory with some explanatory resources, explanatory power, that would make it more plausible by inference to the best explanation. On the other hand, Occam's out there with his razor saying multiplicity per se is a bad thing, right? If you can avoid it, you should. So it's going to cut against you, right? So what I want to do is think about the explanatory power of multiplicity and those kinds of arguments. Now, let me just say a word about Occam's razor. I think the razor, if you actually try and write it down and try and think about it it's very hard to write down a principle that actually holds up very well in the history of science. Because if you read the principle as saying, don't multiply entities unless you absolutely have to, we do it all the time, right? You don't absolutely have to believe that the world existed 5 minutes ago, right? Could have just come into existence. All of us sitting here with these false memories and everything. That's in one straightforward sense, a less populated universe than the one we think we live in. But nobody would think, therefore, you ought to believe it, right? If I'm trying to explain electromagnetic phenomena and I postulate an electromagnetic field, some other person might come along and say, I don't need an electromagnetic field. I've got a direct action at a distance theory. People have tried to do this. Wheeler and Feynman tried to do this. I think it's very implausible to say, well, you ought to believe the guy who doesn't have the electromagnetic field because he's got less, right? It's not always the case that less is more. So there are, of course, bad theories with lots of stuff in it. There are bad theories with too little stuff in it, right? So you really have to think of the evidential situation in each particular case. So what I want to do is look at the way we use multiplicity in explanations. And this is very deep and very puzzling in some way, and again, goes far beyond the issues of cosmology here. In fact, I'll mostly not be talking about cosmology. So suppose I have a multiplicity, this kind of multiplicity, even where it's a multiplicity not of actual things, but merely possible things. One thing we ask is there some natural measure over this set of things so that we can ask what a typical one is like, what most of them are like, okay? And in many cases, we think we can do it in a natural way. This is certainly true in statistical mechanics. There's a natural measure over the state of all possible states, microstates of a system. David called it Lebesgue measure. I have a bee in my bonnet about that because Lebesgue measure is a mathematical measure. Call it the natural measure. It's associated with the measure of space, which we think it's natural because we think space has this geometrical structure. If you have such a measure over this space, you can then ask, are there some features that overwhelmingly most or almost all of those states have? And the situation seems to be, and intuitively there's a great pull to this, is that if you can show some feature is typical in that sense, then the fact that the actual world has it stands in no further need of explanation. Okay, so let me just pause there. That's the basic move. if it's typical, if almost all the ways you could make a world would be like this, then we think my explanatory job for explaining why the actual world is like this is over. Okay, I don't need to invoke anything more. The standard example of this is in statistical mechanics, and this is where I want to talk about thermodynamics for a little while. So suppose we have, and this is, again, a sort of standard story, we have a box of gas. It starts out in some low entropy state. Like, for example, we put all the particles on one side of the box, and then we remove the central wall, so now the box is open. Right now, I'm not asking how it got into that low entropy state. I'm just assume that it starts out in a low entropy state. Boltzmann initiated a kind of scientific program for explaining why it will behave, why boxes of gas behave in very predictable ways. They obey the ideal gas laws, which are stated at the level of these macro conditions of pressure and temperature and so on. I mean, and again, it should astonish you. In a way, it's astonishing. When I characterize a box of gas just by giving you the pressure, the volume, and the temperature, they're almost, think of all the degrees of freedom there are in specifying the exact microstate, right? 10 to the 26, whatever you like, some huge number of degrees of freedom to tell you what's really going on in that box of gas. And I only give you 3 numbers. And the actual microphysics needs every single one of those 10 to the 26 numbers to work, right? That's what I've got to feed into the microphysics to get it to make a prediction. But somehow I can just give you these 3 numbers or 4 numbers, and you can make really good predictions. Right? It's an amazing fact, and it's a fact, right? It's something we have to understand. So how do we do it? Well, Boltzmann's approach was to say, suppose I can show in this way that I characterize my initial state macroscopically, that overwhelmingly most of the microconditions in the box of gas will lead, by these microscopic laws, to a certain kind of behavior, right? That it'll go from this lower entropy state to a higher entropy state, and it'll go at a certain rate, and so on. Lots of things you could show will be typically the case for microconditions. That is just a mathematical fact. Notice what I've just claimed to you is not a physical claim, it's a mathematical claim. It's relative to this measure, overwhelmingly most of these microconditions do X. So suppose I could prove that. That is, as Detlef Durr likes to say, we are actually infinitely far from proving that mathematically for any system. We always have to make approximations and so on, give plausibility arguments to actually get this result. But that's the mathematical result we think holds. Now the question is, what follows from that mathematical result? What follows from the fact that overwhelmingly most of the microconditions compatible with this state do something? Boltzmann's project relies on the contention that if an actual system behaves in this typical way, and again, I've defined typicality mathematically. I haven't cheated by saying by typical I mean that's what things usually do, right? It's purely mathematical. If it behaves that way, then our explanatory project is over. We can say we now understand why. Okay? And then if that's right, then we now understand why boxes of gas do what they do. And so this is a way of appealing to typicality to explain things. Now, if we accept that theories are more plausible if they explain more of what we observe, and that showing that some behavior is typical, according to the theory, makes that behavior explicable without further ado, then, it seems, a theory is more plausible, other things being equal, if it renders the observed features of the universe typical. That I take to be the basic structure of explanatory project here. However, you then think if you're going to do that, it ought to be able to cut against a theory just as well. So there ought to be, just as I define a notion of typicality, there ought to be a notion of atypicality, right? So if overwhelmingly few of the states do something, then you can call that behavior atypical. So you might think that this judgment of typicality is, as it were, just like a theory making a prediction. And if the theory makes a prediction and the prediction comes out correct, counts in favor of the theory. If the theory doesn't make the prediction or predicts something opposite, then that counts against the theory. So this is if you follow this line of reasoning, you'd say, well, gee, if there's behavior, if you observe something that's atypical, if you find all the time systems are doing something that is not displayed by most of the states, then you should decrease your confidence in the theory. And that thought, I think, underlies the fine-tuning arguments, right? So the fine-tuning arguments suggest that without any further added parts to it, if we take the sort of standard Big Bang theory where there's only one Big Bang and the constants of nature are just constant, then it's very atypical to have a universe like that where stars form, where galaxies form, where life can emerge, where complexity can emerge, and so on, right? And therefore, that should render that theory very implausible, okay? Right, so we now say that the typical realization of these laws relative to choices of constants of nature don't contain all of this structure, then there's something wrong with Big Bang cosmology, or the standard Big Bang cosmology anyway. The one where there's only one universe, it's the one we see around us. Now, the situation, however, and this is not to do with cosmology, is more complicated than this. So, even in standard thermodynamics, it doesn't work that way. It's not as if nature, if what we see around us is highly atypical, we reject the theory which rendered the judgment that it's atypical. Why not? Well, and this is, again, a standard problem that happened in thermodynamics, because it's true that if we look at boxes of gas around us, we'll find that their behavior in the forward direction of time is typical. But their behavior in the backward direction of time, that is, if I take their present macro state and in the same way, just ask what is typical, what do most of the micro conditions consistent with that do if I look backward in time? What do most of them do? The answer is they do not behave the way we think gases behave, right? This was the problem that David was worried about. Okay? So just as overwhelmingly most of the micro conditions of a gas not in equilibrium yield increasing entropy as time goes forward, they also yield increasing entropy as time goes backward. But what we don't do, so you might say, well, that's just a refutation of Boltzmann, right? If the success of Boltzmann was getting entropy right in the forward direction, him getting it massively wrong in the backward direction is just as bad a failure. We have to reject his approach. That's what you would do if these typicality judgments were really like predictions. Right? That is, you'd say, great, this theory got prediction A right, good for it, but gee, it got prediction B massively wrong, sorry, right? The theory must be wrong. That's not what happens, and this is the thing I want to point out. This is just, the logic of it is different. You can trump these typicality judgments. There can be other features. It's not like a prediction. So what's really going on? So what's the effect of finding that the universe is atypical? What do we do? In the case of thermodynamics, what we say is the typical behavior doesn't require any further explanation. Atypical behavior does require further explanation. Okay? So this is why it's not like getting a refuted prediction. If you make a prediction and it's wrong, it's just wrong. There's nothing you can do about it. If the behavior is atypical, you say, well, I certainly haven't explained it yet, but there's room there for saying, okay, I need more explanatory principles. And the key question is, what kind of extra explanatory principles are acceptable? What can do the job of rendering this behavior okay? Now, the way we've done this in the observable universe about entropy is we say, well, what explains the atypicality of the present microstate of the universe is the low entropy Big Bang. It's if we grant that the present state of the universe evolved from this low entropy state, then it will of necessity be a very atypical microstate now, because it'll be a state which, if I evolve it backward in time, goes low entropy. Okay? So the fact that the present microstate of the universe is atypical with respect to evolution to the past is accounted for by etiology, right? It's accounted for by explaining how that state came into existence, given the Big Bang. Now, you might say, okay, I've just passed the explanatory buck back to the Big Bang. Now you've got to, explain the Big Bang. Fine, that's true. But notice, all I'm saying is that granting me the Big Bang, I have explained the thing that I thought was puzzling. Okay? So we might ask of the Big Bang, why is it the right kind of state to appeal to account for the typicality? Why do we think that's okay? And what about the Big Bang? Can we explain it in turn? Can we show that it's implied by some other explanatory principle? Can it be shown to be in its own way typical? Can we get into an explanatory regress? And so on. So I think these are the kind of problems everybody is vaguely aware of. I'm just trying to tighten them up. Now, I have to say here, because it's relevant to direction of time, I think when you say it's the etiology of the present microstate that explains why it's atypical, it's really important that you think of time as going from past to future. That there's a preferred direction of time, there's a preferred relation of cause and effect. I think if you tried to do the same thing with the final state of the universe, if you said, the present state seems to be very atypical, why is that? And you said, well, that's because in 100,000 years from now, in the future, such and such will occur. We would reject that. That would be going to the bad kind of teleology that I take it physics is happy to have gotten rid of. Now, I may get a lot of argument about that, but I think that's a fact of the way actual cosmologists, if you went to a cosmologist and said, I'll explain this by telling you it's like this because in another 100,000 years it'll be like that, they would just say, no, that's not an explanation at all. It's the wrong way around. I think that's right myself. That's what I mean by getting rid of teleology. Appeal to future states to explain the present state. So if that's right, and you want to explain the Big Bang, well, you can't explain it by referencing anything after it. You'd have to have something before it, or you'd have to have some timeless principle or some other kind of principle that doesn't require cause and effect to give you, to end the explanatory regress. Now, in standard Big Bang theory, that is the one without multiplicity, there's only one universe and the constants are just independent degrees of freedom, we say that renders the existence of galaxies, planets, and life highly atypical. And then on this view, that means we now either need to have an entirely new theory, which is a possibility, or find some principle we can add that trumps the atypicality. It might involve new physics. It might be some compelling principle. We think compelling principle about the nature of the Big Bang or some new dynamics and so on. But the idea of a multiverse is to say, no, I'm going to solve this thing without doing that. I'm going to turn this whole atypicality situation on its head. So, and again, I take it it's kind of obvious how this goes, but let's go through it in steps. So we've got a multiverse. We've now gone from the standard picture where there's only one universe to one there are lots and lots of them. And not only lots and lots of them, but lots and lots of them with different choices for the constants of nature, if you will. And now we add the anthropic filter. And I know the anthropic principle has been, in some sense, very controversial, but in this application, I think it's completely uncontroversial, completely straightforward. Nobody can complain about it. Here's the strategy. You make it explicit. So you adopt a physics whose dynamics yields a large enough multiverse, and the different regions are a random sampling from the space of initial conditions and constants of nature, then the existence of at least one region, right, that at least one region will exist capable of supporting galaxies, planets, and life, may in fact be rendered typical. Right? So we're going back to saying, I'm going to explain it by it being typical. It will be typical in any multiverse. In a typical multiverse, there'll be at least one region, right, one universe that has the right features. So then we don't, if that's right, then we don't need to worry about the initial conditions of the multiverse, because the idea is that start the multiverse off pretty much however you like. However you do, it's going to grow all these different pieces. These different pieces will have this multiplicity, and at least one of them will have the right conditions. Then we have the anthropic filter, right? It may be that among all these regions that are produced, stars and so on, galaxies are very, very sparse. Very few regions have it, so you might sort of jump to the conclusion that it makes it very improbable that we should find ourselves in the special region, right? That we should have won the lottery. But again, 2 seconds thought and you see that's wrong. Evidently, it's necessary that every living observer should find itself in a region that supports life. So long as the theory makes the existence of some such regions highly probable, the sparseness becomes completely irrelevant. Right? That's not a black mark against the theory. It doesn't matter how often they occur. But now we can push a little further. We can push the typicality further. We can now ask for, well, what about typical inhabited regions? So I now have a multiverse. I've created a multiverse. It will almost certainly produce inhabited regions, in fact, lots of them. What can we say about overwhelmingly most of them, right? If we could find a decent measure, if we could find a decent way to make good sense out of overwhelmingly most, and these are technical problems we'd have to deal with, we could then say we ought to expect that we live in a typical such region, right? So now we're back again to now the theory can start to explain a lot of stuff. Notice, and so this is this kind of jujitsu thing, the methodological situation is now completely flipped over, right? That is, the greater the restrictions that are needed for life, assuming I have a big enough multiverse, the greater the restrictions, the more explanatorily powerful the theory becomes, right? Because if, in order to support life, there's only a very ranged set of values, then you can say, well, in a typical region that does support life, the values have to be in this very special range. And look, they are, right? It's, again, kind of a quasi-prediction of the theory. So the entire methodology has now been inverted, okay? Well, now you might say, isn't this too good to be true, right? Is this an explanatory free lunch, right? You might think, look, I've just given you a reason to maximize your multiplicity, right? To come up with theories that just produce as much as possible. And apparently at no cost, right? Because then, gee, whatever you see, you can now explain, and so we're anti-Occam to the nth degree. But that's not right. So this is the last point I really want to get to, and it's very subtle and it's very interesting, it's very difficult. You can have too much multiplicity, right? You can go too far. Your multiplicity can start to cut against you at a certain point. Here's the classical example, and this goes back, and it goes back before this cosmological, the modern cosmological stuff. It's been discussed, and it was discussed in the context of trying to explain the low entropy character of the Big Bang, or the low entropy character of the early parts of our universe. One suggestion for accounting for the low entropy state goes back to Boltzmann, and this is in 1897. He discusses the choice between, he talks about the choice between two pictures. One picture is that he says we can accept a unidirectional change of the entire universe from a definite, by which he means low entropy initial state, to a final state. So he might say one picture is the whole universe starts in a low entropy state. I've given you reasons to expect any such state typically to evolve in a certain way. It does evolve in that way. You end up in a high entropy state. End of story. On the other hand, he says there's another picture you could imagine. So this is just the quote. One can assume that the entire universe finds itself at present in a very improbable state. However, one may assume that the eons during which this improbable state lasts and the distance from here to Sirius are minute compared to the age and size of the universe. There must then be in the universe, which is in thermal equilibrium as a whole, and therefore dead, here and there relatively small regions of the size of our galaxy, which we call worlds, which during the relatively short time of eons deviate significantly from thermal equilibrium. The objection that it's uneconomical, right, here Occam, the objection that it's uneconomical and hence senseless to imagine such a large part of the universe is dead in order to explain why a small part is living, this objection I consider invalid. I remember only too well a person who absolutely refused to believe that the sun could be 20 million miles from the Earth on the grounds that it's inconceivable there could be so much space filled only with ether and so little with life. Okay? I mean, this is really beautiful, right? This is exactly the problem. So this is a kind of, this isn't quite right, I got this off the web, but this is the picture of a Boltzmann kind of closed box universe that exists forever, and this is the entropy curve. And the idea is that the regions at the top, very near the top, should actually be much longer. Most of the time, this universe would be in thermal equilibrium. But it randomly fluctuates in the way that you would predict, and these fluctuations can be deeper or more shallow. And the point about this curve is that the shallow fluctuations are much more frequent than the deeper ones. The deeper the fluctuation has to go, the more rare it is. So here's our present entropy, say it's somewhere, imagine the actual universe's entropy is up here. What we think is that the past, the entropy was much lower. And we got here by climbing up that entropy gradient. Now, Boltzmann, so notice, Boltzmann's picture contains an infinite multiplicity of worlds, what he calls worlds, and can essentially guarantee the existence of a world that corresponds to what we see around us. You might say, okay, at least one world like ours will exist, according to Boltzmann. However, and this is the key point, Feynman has argued, again, the argument is really convincing, but it's very puzzling. He's argued that Boltzmann's picture contains too much multiplicity. Right? There's too much stuff in it to be credible. We can't believe it. For the typical world, here's Feynman's argument, that the typical world that looks like our present surroundings, so take into account that we're here in this room, that all this stuff is going on, that the Earth is here, everything we think we know, the typical world, again, if we go back here, go up here at the blue curve and pick out all the worlds up there that look like our present world, okay? As far as we can tell. The typical world does not behave in the way that our world behaves. In particular, the typical world in this group that matches our present surroundings has not evolved from a much lower entropy Big Bang state and will not continue to display the observable characteristics we expect of our world. That is, the actual predictions for what you'll see are different for the typical world and for ours. In what way? So here's Feynman. Here are just the quotes. He imagines a world, he says, imagine a world just white and black particles in a box. And you notice in a region, they're separated. The white is separated from the black, and you have two hypotheses. One hypothesis is that it all started out separated, all the white on one side and all the black on the other, and it's slowly remixing. And the other is, no, it started out in equilibrium. It started out with all the white and black mixed together, but there are fluctuations, and here and there, by chance, the white and black will become separated out. So Feynman says, one possible explanation of the high degree of order in the present-day world is that it's just a question of luck. Perhaps our universe happened to have had a fluctuation in the past in which things got somewhat separated, and now they're running back together again. We'd like to argue that this is not the case, right? That we haven't fluctuated to our present situation that way. Suppose we do not look at the whole box at once, but only at a piece of the box. Then at a certain moment, suppose we discover a certain amount of order. In this little piece, black and white are separate. What should we deduce, or what should we expect, you might say, about the condition in places where we've not yet looked? If we really believe that the order arose from complete disorder by a fluctuation, we must surely take the most likely, read their typical, fluctuation, which could produce it, right? Take the typical one that leads to that. And the most likely condition is not that the rest of the world has become disentangled. Therefore, from the hypothesis that the world is a fluctuation, all of the predictions are that if we look at a part of the world we've never seen before, we'll find it mixed up and not like the piece we just looked at. If our order were due to a fluctuation, we would not expect order anywhere but where we've just noticed it. Now, if we assume, on the other hand, the separation is because in the past the universe was really ordered, that is, entropy in the past was much lower than today, it's not due to a fluctuation, but the whole thing used to be black and white, right? Used to be separated out. This theory, this different theory, now predicts that there will be order in other places. The order is not due to a fluctuation, but due to a much higher ordering at the beginning of time. Then we would expect to find order in places where we've not yet looked. So notice, these two approaches lead to different predictions. And then he says that the astronomers, I mean, Priya will tell you this, what Feynman says is correct here. The astronomers, for example, have only looked at some of the stars. Every day they turn their telescopes to other stars, right? And they see stars, right? This is an amazing thing, according to the fluctuation theory, this is an amazing thing. You turn your telescope where you haven't looked before and you still see stars, right? The new stars are doing the same thing as the other stars. We therefore conclude that the universe is not a fluctuation, and that the order is a memory of conditions when things started. This is not to say we understand the logic of it. I actually, as you see, I really like that last statement. Yeah. Okay? So let's pause. What did Feynman just do? Because what he did is really convincing. What did he just do? The large stars, just like all the other stars that we've seen, we can get convincing evidence that the Boltzmann picture is wrong, right? That's not the way the universe is. So just by looking around us now, we can become convinced that the overall multiverse of Boltzmann does not exist, right? Too much multiplicity. even though it contains parts that are just like everything we see. Now, we can take this argument further, and this is the last thing I'm going to talk about, and you'll see why they're called Boltzmann's brains. So Feynman's reasoning, which seems quite solid, can be extended to a more radical direction so that we can get strong evidence about the overall structure of the universe, not by pointing telescopes. So we could ask Priya to go check. Maybe it's a fluctuation, right? And she has to run and check her telescope. Okay, look at a star nobody's ever looked at before. We can actually do this experiment right now. Okay? By making the most mundane observations we can make here in the room with no special apparatus. This application of the same structure of argumentation is known as Boltzmann's brain. So let's go back to the earlier diagram, but let's make this change. Instead of looking at the present overall state of the world as we think it is, say in the room, just look at your present brain state. Right? Your brain is now in some state. I'm assuming that your present phenomenology and everything else is a function of that state. And so in the Boltzmann universe, now let's pick out all the points where there are little regions of the universe with brains like yours. Okay? And again, here's the past. We think that we got here through this long climb up a long entropy gradient. Okay? But there are lots of brains like yours that didn't get there that way. So what is a typical brain, just like yours right now? What is a typical brain like? Well, the argument that we started with before, we now proceed in the same way, but with your present brain state, which we assume determines your experiences and apparent memories and so on, playing the role that the present state of the whole observable universe did before. Given the Boltzmann multiverse, the typical brain in such a state came about by a minimal fluctuation from equilibrium, because the fluctuations are less likely the deeper they are. But the minimal fluctuation would create just the organized brain and nothing else organized. It wouldn't create a body, wouldn't create a room, wouldn't create a heart, wouldn't create a circulatory system. Okay? Got your brain state, so everything looks, brain in a vat, but no vat. So, on that theory, a typical brain in this universe that's in an identical state to yours right now is just about to die. Right? Overwhelmingly most of them throughout the multiverse will not exist as functioning brains in a second. So let's do an experiment. Okay? Experiment over. How did I know it was going to work out that way? Since we all survived, we know that we're not Boltzmann's brains, as I just described them, right? We're not disembodied brains without circulatory systems floating around, blah, blah, blah. Okay? So, it seems, we know it's not the case that a typical brain in your brain state is a Boltzmann brain. So, we know something about the distribution of states of functioning brains throughout the whole multiverse. In fact, we seem, again, to have shown that any hypothesis about the structure of the physical universe that entails that most functioning brains are Boltzmann brains is almost certainly false. We've ruled out a huge class of possible multiverse theories and theories with a single universe in which most brains are Boltzmann brains. So we've, all of these I've now said, I've just given you a little experiment that shows you all of those theories are wrong. So a multiverse theory can have too much variety to be acceptable as a physical theory. But, and again, I'm just honestly giving you puzzlement, right? I am convinced by these arguments, but then I stop and look at them, and I'm puzzled by them, right? It seems like somehow we've proven way too much, right? Consider, suppose someone right now proposes to you the following theory of the long-term future of the world. The world and time itself began with a low-entropy Big Bang, like the one we think occurred, but the world is a closed system that will eventually, after quadrillions of years, come to equilibrium, then undergo fluctuations, as Boltzmann describes. That state will persist forever, right, this fluctuating state. Therefore, over the whole of infinite time, overwhelmingly most brains will be Boltzmann brains. This is a hypothesis about the distant future. But by Feynman's argument, it looks like we just effectively refuted it, right, by making a rather trivial experiment now. I'm done. This is okay. This is my last slide, right? So that's why I like the last thing Feynman said. Right? So the argument about Boltzmann brains involves what philosophers call self-locating beliefs. So it's, you know, beliefs about where you are in a larger thing. And there hasn't been much agreement, maybe you'll understand why, among philosophers about how to evaluate these arguments, how to make judgments about probability in these cases, when you're asking, well, what's the likelihood you're one or another of various brains in the same brain state? Fortunately, I think, these are not the main arguments that are supposed to convince us of a multiverse, because I think if they were, they are very puzzling. Arguments from direct observational effects of other universes and for a multiverse structure as a consequence of a theory that's accepted for more standard empirical reasons don't depend on these sorts of considerations, but I think we would do well to reflect further on the logic of these arguments. Thank you.